Hi there, and a heartfelt welcome. I'm so happy you've joined me today. Before we dive in, I'd love it if you could share in the comments where in the world you're tuning in from and what time it happens to be for you right now. It's always so special to see our little community connecting across time zones. A gentle thank you as well to everyone who has already subscribed and shown love with likes on the videos. It truly makes a difference. And if you have ideas or topics you'd like me to cover, please let me know in the comments. With that, let's get started. Chapter 1. Understanding Black Holes, Nature's Enigmas. In the vast expanse of the universe, black holes stand as nature's most mysterious objects. These enigmatic phenomena challenge our understanding of physics and stretch the imagination. They are not merely voids in space, but rather regions where gravity exerts an unyielding pull. Once formed, they hold the potential to reshape everything around them. A black hole is defined by its ability to trap light, creating a point of no return beyond which nothing can escape. This characteristic arises from their incredible density, which compresses matter into a small area. The boundary surrounding a black hole is known as the event horizon. It marks the threshold that separates the observable universe from the secrets held within. As physicist Stephen Hawking elegantly stated, black holes are not the end of the universe, but rather a doorway to understanding it. There are several types of black holes, each with unique properties and formation processes. Stellar black holes are perhaps the most familiar to us. They form when massive stars exhaust their nuclear fuel and undergo gravitational collapse. This process results in a core that collapses under its own weight, creating a black hole that can have several times the mass of our Sun. Supermassive black holes, on the other hand, reside at the centers of galaxies and can have masses equivalent to millions or even billions of suns. Their origins are still a subject of active research. Some theories suggest that they formed from the merging of smaller black holes, while others propose that they grew from massive clouds of gas in the early universe. Imagine the immense gravitational pull these giants exert on their surroundings, influencing the orbits of stars and the formation of galaxies. Primordial black holes are a more speculative type, theorized to have formed shortly after the Big Bang. They could vary greatly in size, from very small to quite large, and serve as intriguing candidates for dark matter. Their existence remains unproven, yet they invite us to ponder the conditions of the early universe and the mysteries that remain hidden from our current understanding. The role of black holes in the universe is profound. They not only serve as cosmic vacuum cleaners, consuming matter, but also play a crucial role in the life cycles of galaxies. They can trigger star formation by compressing gas and dust, creating new stars in their wake. As astronomer Andrea Ghez expressed, supermassive black holes are like the engines of galaxies, driving their evolution. Historically, the concept of black holes has evolved significantly. The term itself was first coined in the 1960s, but the ideas surrounding them trace back much further. In the early 18th century, the notion of a, quote, dark star was proposed by the British natural philosopher John Michell. He speculated that if a star were massive enough, its gravitational pull could prevent light from escaping. This early vision foreshadowed the discoveries that would come centuries later. Albert Einstein's theories of relativity laid the groundwork for understanding black holes. He introduced the idea that massive objects warp the fabric of space-time, leading to the conception of black holes as regions where this warping becomes extreme. The solutions to Einstein's equations revealed the potential for singularities, points of infinite density hidden within black holes. As we journey through the history of black holes, we encounter the groundbreaking work of physicists like Roger Penrose and John Archibald Wheeler. Penrose's singularity theorem provided a mathematical foundation for understanding how black holes could form from collapsing stars. Meanwhile, Wheeler popularized the term black hole and explored the relationship between black holes and information. In recent decades, our exploration of black holes has intensified. The first image of a black hole's shadow was captured in 2019, revealing the silhouette of the supermassive black hole at the center of the galaxy M87. This monumental achievement is a testament to human ingenuity and our relentless pursuit of knowledge. As we gaze at that image, we are reminded of the vastness of the universe and our place within it. Isn't it awe-inspiring to consider how black holes challenge our understanding of reality? They compel us to think deeply about the nature of existence and the boundaries of our knowledge. Each discovery brings us closer to unraveling the intricate mysteries of the cosmos. In the grand tapestry of the universe, black holes serve as reminders of the delicate balance between creation and destruction. They are not merely voids, but rather dynamic entities that influence the cosmic landscape. As we continue to uncover their secrets, we are drawn into a deeper understanding of the universe and our role within it. Imagine standing before a black hole, feeling its immense gravitational pull. It is a gateway to the unknown, a portal that invites exploration and curiosity. The journey to comprehend these enigmatic structures is just beginning, and the questions they pose are as endless as the cosmos itself. The very essence of a black hole lies in its definition. A black hole is a region in space where gravity is so strong that nothing, not even light, can escape its pull. This remarkable phenomenon arises from the collapse of massive stars, where, under the relentless pressure of gravity, the star implodes upon itself. When such a star exhausts its nuclear fuel, it can no longer support its mass, leading to a dramatic transformation. The core collapses while the outer layers may explode in a supernova, leaving behind a singularity, a point of infinite density, and an event horizon, the boundary beyond which nothing can return. Consider the enchanting yet daunting nature of these entities. Isn't it fascinating that the gravitational force of a black hole warps space-time itself? It creates a well in the fabric of the universe, inviting us to ponder the very nature of existence. The event horizon, which defines the limits of a black hole, marks the threshold between the known and the unknown, a barrier that beckons exploration. Black holes come in various forms, each captivating in its own right. Stellar black holes, the most common type, form from the remnants of massive stars. They typically have a mass ranging from a few to several tens of times that of our Sun. Then there are supermassive black holes, which lurk at the centers of galaxies, harboring masses equivalent to millions or even billions of suns. Their formation remains a subject of intrigue. Possibly, they evolved from the merging of smaller black holes or from the direct collapse of massive gas clouds in the early universe. Imagine a creature so titanic that it holds sway over entire galaxies, its gravitational grip shaping the orbits of stars. Among the lesser-known but equally captivating types are primordial black holes, theorized to have formed shortly after the Big Bang. These enigmatic structures could have masses varying widely, potentially even as small as an asteroid or as large as a star. Their existence could provide valuable insights into the conditions of the early universe and the nature of dark matter. What wonders might these primordial entities hold, lurking in the vastness of space, unseen yet profoundly impactful? Black holes play a crucial role in the cosmic theater, acting as engines of galactic evolution. They influence the formation and growth of galaxies, shaping the very structure of the universe. The gravitational forces exerted by a supermassive black hole can regulate star formation within its host galaxy, either fostering or stifling the birth of new stars. Imagine the delicate balance these cosmic giants maintain, orchestrating the birth and death of stars, guiding the dance of celestial bodies across the cosmos. The historical journey of our understanding of black holes is a rich tapestry woven from the insights of brilliant minds. In the early 20th century, Albert Einstein's theory of general relativity laid the groundwork for comprehending gravity as the curvature of space-time. It was his equations that hinted at the possibility of these mysterious objects, yet it took decades for the scientific community to fully embrace the concept. John Archibald Wheeler, a pivotal figure in the field, famously described black holes as, quote, the most perfect bits of the universe. He emphasized the profound implications of their existence, asserting that they challenge our notions of reality. As he eloquently stated, black holes aren't holes at all. They are massive, gravitational wells that trap everything nearby. These insights have inspired generations of physicists to delve deeper into the nature of black holes and their implications for the universe. Theories about black holes have evolved over time, fueled by both observation and imagination. In the 1970s, Stephen Hawking introduced the groundbreaking idea of Hawking radiation, suggesting that black holes are not entirely black, but can emit radiation due to quantum effects near the event horizon. This revelation sparked a revolution in our understanding, raising questions about the fate of information and matter consumed by black holes. How could such formidable entities allow for the possibility of escaping their grasp? As we ponder these cosmic riddles, it becomes clear that black holes are not mere voids. They are profound mysteries that challenge the very foundations of physics. They embody the intersection of relativity and quantum mechanics, inviting us to explore the boundaries of our knowledge. The quest to understand black holes is a journey of discovery, one that transcends mere observation and touches upon the philosophical implications of existence itself. Imagine the thrill of peering into the abyss, contemplating the gravitational pull that shapes the cosmos. As we delve deeper into the nature of black holes, we are drawn into a world where time and space intertwine in ways that defy our understanding. The pursuit of knowledge, fueled by curiosity, propels us forward into the unknown. The interplay between black holes and the fabric of the universe raises profound questions about the nature of reality. Are they mere destroyers, erasing all that ventures too close? Or do they serve a greater purpose in the cosmic order? The balance between creation and destruction is a fundamental aspect of the universe, and black holes are at the heart of this dance. As we stand on the precipice of discovery, the allure of black holes continues to captivate our imagination. Each revelation beckons us to explore further, to question our assumptions, and to embrace the mysteries that lie beyond. What lies within the heart of a black hole? What cosmic secrets await us in the depths of these enigmatic structures? The journey of understanding black holes is a testament to human curiosity and resilience. With each new observation, we peel back the layers of the universe, revealing the intricate mechanisms that govern its workings. The quest for knowledge is an endless journey, one that reminds us that the universe holds infinite wonders waiting to be uncovered. As we reflect on the nature of black holes, we are reminded that we are but small parts of a grand cosmic narrative, a story that continues to unfold with every passing moment. The exploration of black holes is a voyage into the heart of the unknown, inviting us to contemplate our place in the cosmos. With every question we ask, we take a step closer to understanding the universe's most profound mysteries. The enigma of black holes is not just a scientific pursuit. It is a journey of the mind and spirit, one that intertwines the fabric of reality with the threads of imagination. What will we discover next in this vast expanse of the universe? The possibilities are as boundless as the cosmos itself. As we ponder the intricate dance of creation and destruction that black holes represent, we find ourselves drawn to a critical threshold, the event horizon. This boundary, shrouded in mystery, beckons us to explore what lies beyond, challenging our understanding of physics and the very fabric of reality. What happens when we approach this enigmatic limit? The implications of crossing the event horizon not only reshape our views of black holes, but also invite us to consider the profound mysteries that await. With our curiosity ignited, we now turn our gaze toward this pivotal concept, ready to delve deeper into the unknown and uncover the secrets that lie at the brink of existence. Chapter 2: The Event Horizon, Gateway to the Unknown. The event horizon, a boundary that embodies both mystery and intrigue, serves as a gateway to the unknown. Imagine standing on the edge of a precipice, where the familiar landscape of reality fades into the unfathomable depths of a black hole. This threshold, this event horizon, marks the point of no return. Beyond it lies a realm where the laws of physics, as we know them, begin to unravel. At its core, the event horizon defines the very boundary of a black hole. It is not a physical surface, but rather an invisible line that delineates the region where escape is impossible. Once an object crosses this boundary, it is irrevocably drawn into the black hole's grasp, unable to transmit any information back to the outside universe. Picture a lighthouse, its beam illuminating the darkness. Yet the moment a ship ventures too close, it disappears into the night, never to return. The implications of crossing the event horizon are profound. For the observer falling in, time itself becomes a curious illusion. According to Einstein's theory of general relativity, as one approaches the event horizon, time appears to slow down relative to an outside observer. Imagine watching a clock tick away as you approach this boundary, each tick stretching into eternity. This phenomenon raises tantalizing questions. What does it mean to experience time in such a manner? Is there a moment when you realize you can never go back? Or is it a gradual acceptance, much like drifting into a dream? Theoretical observations of event horizons have captivated many brilliant minds throughout history. The concept was brought into popular discourse by physicist John Archibald Wheeler, who famously noted, "Black holes have no hair," referring to the idea that they can be fully described by only a few parameters: mass, charge, and angular momentum. This simplicity amidst complexity speaks to the astonishing nature of these cosmic enigmas, where the intricate details of what lies within vanish behind the event horizon. Imagine the event horizon as a cosmic curtain, shielding the mysteries within from our gaze. Theoretical physicists have speculated about what might occur as one crosses this threshold. Some suggest that a traveler might encounter a world of infinite density, while others ponder the possibility of alternate realities. The event horizon thus serves not only as a boundary, but also as a portal to realms beyond our comprehension. As we delve deeper into the fabric of this cosmic enigma, we begin to consider the possibility of what happens to information that crosses the event horizon. If nothing can escape, what becomes of the data, the essence of the matter that once was? This question has sparked debates among scientists, leading to the formulation of theories that challenge our understanding of reality itself. Stephen Hawking, a luminary in the field, proposed that black holes could emit radiation, now famously known as Hawking radiation, suggesting that information might not be lost forever. His assertion invites us to ponder, could there be a way to recover what we believe to be lost? The implications of this idea ripple through the fabric of theoretical physics, igniting discussions about the very nature of reality. Moreover, the event horizon serves as a critical focal point for understanding the universe's fundamental laws. As we observe the behavior of matter and energy near black holes, we are afforded glimpses into the interplay of gravity, time, and quantum mechanics. The event horizon not only challenges our perceptions, but also offers opportunities to test the limits of our current scientific paradigms. Let us take a moment to visualize the vastness of the universe, where numerous black holes exist, each with its own event horizon. Each one represents a unique story, an unfolding narrative that remains largely untold. As we peer into the night sky, we may wonder what secrets lie beyond these boundaries, waiting to be discovered. In this dance of curiosity and wonder, the event horizon remains a tantalizing frontier. It is a reminder that there is so much we have yet to understand, much like the horizon at sunset, where the sun kisses the earth and promises that another day will dawn. What lies beyond that horizon? What mysteries await those brave enough to approach it? As we explore the depths of our cosmic ocean, the event horizon stands as a beacon, illuminating the pathways to the unknown. It invites us to ask questions, to seek answers, and to embrace the beauty of uncertainty. In this pursuit of knowledge, we find ourselves woven into the very fabric of the universe, connected to the stars and the mysteries they hold. The journey through the cosmos is as much about the questions we ask as it is about the answers we seek. The event horizon, with its tantalizing promise of discovery, beckons us to continue exploring, to delve deeper into the unknown. It teaches us that the boundaries of our understanding are not the end, but rather the beginning of a grand adventure, one that challenges us to expand our horizons and embrace the mysteries of existence. As we contemplate the notion of the event horizons, let us remember that every question opens a door to new possibilities. Each inquiry leads us further into the realms of imagination and discovery, where the unknown becomes a canvas for our curiosity. What will we find as we venture closer to these edges of reality? What stories will unfold as we dare to cross the event horizon? In this vast universe where black holes loom and the event horizon defines the boundaries of our understanding, we are reminded of the fragile beauty of existence. Each moment spent pondering these cosmic wonders is a moment well spent, a testament to our enduring quest for knowledge and connection. The event horizon is more than a scientific concept. It is a symbol of our relentless pursuit of the unknown, inviting us to explore the depths of our own consciousness as we gaze into the infinite expanse of the cosmos. So, dear listener, as you reflect upon the event horizon and all it represents, let your imagination soar. Picture the swirling galaxies, the shimmering stars, and the mysteries that lie beyond the boundaries of what we know. Embrace the journey into the unknown, for it is in that exploration that we may find not only answers but also the very essence of our existence. The event horizon stands not merely as a barrier, but as a reminder of the beauty and wonder that awaits us in the uncharted realms of the universe. As we immerse ourselves in the concept of the event horizon, we must recognize its role as the boundary that delineates the known from the unknown. Imagine a vast ocean under a starry sky, where the waves gently lap against the shore, each ripple a question waiting to be answered. The event horizon, in this analogy, is the invisible line that separates the tranquil waters of understanding from the tumultuous depths of mystery. Once crossed, light itself cannot escape the gravitational pull of a black hole, rendering the event horizon a one-way street into the unfathomable. The implications of crossing this boundary evoke both fear and fascination. The moment one passes the event horizon, they are enveloped by a gravitational embrace, so intense that time and space themselves begin to distort. It is as though one has stepped into a realm where the familiar rules of physics unravel, leaving only whispers of what once was. This distortion raises a profound question. What lies beyond this threshold? Theoretical observation suggests that the view from the event horizon might be unlike anything we can imagine. As one approaches this boundary, the universe outside becomes increasingly compressed, its light bending and warping under the influence of gravity. Picture yourself standing on the brink of this cosmic precipice, where stars twinkle like distant diamonds, their light stretched and elongated, creating a breathtaking yet eerie panorama. Acclaimed physicist Kip Thorne once remarked, "The black hole is the most beautiful object in the universe." His words capture the allure of these enigmatic entities, inviting us to ponder their secrets. If black holes possess such beauty, what mysteries do we uncover as we delve deeper into the nature of the event horizon? As we explore these questions, we encounter the notion of time itself, a concept that behaves in unexpected ways near the event horizon. According to Einstein's theory of relativity, time slows down in the presence of strong gravitational fields. Imagine a clock ticking away on Earth, while another, positioned just at the event horizon, ticks at a different pace. For an observer outside, it may appear as if time stands still for the one who has crossed into the black hole's domain. This revelation sparks a contemplation. If time is so malleable, what does it mean for our understanding of existence and mortality? The event horizon is not merely an abstract idea, it carries with it the weight of profound implications. It serves as a reminder of our very limitations, an invitation to confront the unknown. Theoretical physicist Stephen Hawking, a pioneer in black hole research, famously stated, "The only black hole I don't like is the one at the center of my own universe." His humor belies a deeper truth. Within the vast cosmos, black holes reflect our own existential dilemmas. They challenge us to confront what we cannot understand and to embrace the uncertainties of life. As we contemplate these cosmic mysteries, we also explore the theoretical framework surrounding event horizons. Imagine scientists peering into the heart of a black hole, their minds racing with the possibilities of what could be discovered. Theories abound that suggest event horizons might not be as impenetrable as they seem. Some physicists propose the existence of wormholes at these boundaries, hypothetical passages connecting distant regions of space and time. What if, by traversing an event horizon, one could emerge in another galaxy, or even another universe? Such notions may seem fantastical, yet they underscore the spirit of scientific inquiry. Each hypothesis pushes the boundaries of our imagination, inviting us to explore the intersection of reality and possibility. It is a tantalizing proposition, one that beckons us to consider the fabric of our universe and the hidden dimensions that may lie just out of reach. Furthermore, the event horizon presents a captivating paradox for scientists. The question of information loss arises with the idea that anything crossing this boundary is lost forever. Yet Hawking's work on black hole radiation introduced the idea that information might be preserved, existing in some form even after it has crossed the event horizon. The implications are staggering. If information can escape in a different guise, what does that mean for our understanding of reality itself? Imagine a universe where knowledge is never truly lost, where mysteries transform rather than vanish. This idea resonates with the essence of scientific exploration, as we strive to uncover the hidden truths of existence. The event horizon then becomes a metaphor for our own journeys, a boundary we approach as we seek to expand our understanding, to challenge our beliefs, and to confront the unknown. As we drift through these contemplations, let your mind wander to the spectral glow of quasars, the brilliant beacons of energy that arise in the vicinity of black holes. These celestial phenomena, fueled by the accretion of matter, present a stunning contrast to the darkness of the event horizon. They remind us that even in the depths of cosmic shadows, there exists a light that illuminates the path of our inquiry. In our quest for knowledge, we must embrace the event horizon not just as a point of no return, but as a gateway to the infinite possibilities that lie beyond. Each exploration leads us to new realms of understanding, where curiosity fuels our desire to seek answers and to delve deeper into the mysteries of the universe. The event horizon stands as a testament to our enduring spirit, a symbol of the beauty and complexity that awaits us as we venture forth into the cosmic unknown. As we navigate the profound mysteries of the event horizon, we find ourselves on the precipice of something even more enigmatic, the singularity that lies at the heart of a black hole. This elusive point challenges our understanding of the universe, presenting a realm where the laws of physics as we know them may unravel. In the next chapter, we will delve into the defining characteristics of singularity and explore the theories that seek to decipher its nature. What happens to space and time in its presence? And how does the immense gravity of a singularity shape our universe? Join us as we journey deeper into this cosmic core, where the very fabric of reality is tested and transformed. Chapter 3. Singularity, the core of a black hole. In the vast expanse of the universe, where the fabric of reality bends and stretches, lies the singularity, a point of infinite density and gravitational pull at the very heart of a black hole. Imagine a realm where the rules of physics as we know them cease to apply, where space and time are transformed into something unrecognizable. A singularity represents not just a physical point, but a profound mystery that challenges our understanding of the cosmos. A singularity is defined as a point in space where the gravitational forces are so intense that space-time curves infinitely. In this peculiar state, the known laws of physics break down. As one theoretical physicist expressed, a singularity is a point where all our equations fail, leading to a void in our understanding. This sentiment captures the essence of what it means to approach a black hole's core. The characteristics of singularity are both fascinating and perplexing. The density reaches unimaginable levels, and the gravitational pull becomes so strong that nothing, not even light, can escape its grasp. Theories surrounding the nature of singularity abound, weaving a rich tapestry of scientific inquiry. Some scientists propose that singularities may be cloaked in a veil of quantum effects, suggesting that the rules governing the very small might illuminate aspects of the very large. What if, instead of a definitive point, singularities are dynamic entities, evolving and interacting with the surrounding universe? This idea invites us to ponder the possibility of a universe where singularities are not just endpoints, but also beginnings of new structures and phenomena. Consider the effects of a singularity on the fabric of space and time. As one approaches this enigmatic core, traditional concepts of distance and duration begin to unravel. Time, as we perceive it, does not flow in a linear fashion near a singularity. Instead, it stretches and warps, creating an experience that is profoundly different from our everyday reality. Imagine standing on the edge of this abyss, where a moment could feel like an eternity, and an eternity could collapse into a fleeting instant. Gravity, the force that binds us to the earth, takes on a new dimension in the presence of a singularity. The relationship between singularity and gravity is one of profound connection. As gravity intensifies, it pulls everything towards the singularity, warping space and distorting time in its wake. The gravitational field is so powerful that it overwhelms all other forces, dictating the behavior of matter and energy in its vicinity. This gravitational force has led to the speculation that singularities might hold the key to understanding not only black holes but also the universe itself. Theoretical physicists like Kip Thorne have posited that the study of singularities could unveil the secrets of time travel, or even the very origins of our universe. Black holes are not the end of the road, Thorne asserts. They are gateways to other realms. As we delve deeper into the mysteries of singularities, we encounter questions that challenge our very existence. What happens to the information that falls into a black hole? Does it vanish forever, or is it somehow preserved in the fabric of the universe? These questions echo through the halls of scientific inquiry, prompting a re-examination of our understanding of reality. In this realm of extremes, where the known meets the unknown, the nature of singularity continues to inspire awe and wonder. It invites us to explore the boundaries of our comprehension and to imagine the possibilities that lie beyond. The singularity, at the core of a black hole, stands as a testament to the complexity of the universe, a reminder that there is still so much to learn and discover. The singularity, a point where the laws of physics as we know them cease to function in any conventional sense, is a phenomenon that challenges our understanding of the universe. At this point, matter is compressed into an infinitesimally small space, resulting in infinite density. Visualize a star collapsing under its own gravity, its core imploding, until it becomes a singularity. As Stephen Hawking eloquently put it, "The singularity is where the laws of physics break down, and we can no longer make predictions." This profound statement reflects the heart of the enigma that envelops singularities. At the singularity, time itself becomes a malleable construct. Imagine time as a river, flowing effortlessly through the landscape of existence. As you approach the singularity, that river begins to twist and churn, creating whirlpools where time may stand still or even reverse. The very fabric of reality is stretched and contorted, leading to scenarios where events can unfold in ways that challenge our intuitive grasp of cause and effect. What does it feel like to exist in a realm where the arrow of time is no longer linear? This conundrum emphasizes the limitations of our current understanding, urging scientists to seek new frameworks to explain the behavior of singularities. Theories surrounding the nature of singularities abound, with different schools of thought attempting to decipher this cosmic riddle. One influential idea is that singularities are not merely destructive endpoints, but rather fundamental building blocks of the universe. This perspective suggests that they might play a role in the creation of new universes, or even the birth of new forms of matter and energy. The concept of a white hole, a hypothetical counterpart to a black hole, is one such theory. While black holes draw everything in, white holes are thought to expel matter and energy, perhaps serving as portals for the universe's continual evolution. As we ponder these ideas, we are reminded of the words of physicist Roger Penrose. The universe is not just a collection of things, but a collection of relationships. This sentiment encapsulates the interconnectedness of singularities with the entire cosmos. They may not reside in isolation. Instead, they may reflect the fundamental nature of space-time itself. This insight leads us to consider how singularities interact with space and time, bending them to their will. The gravitational influence of a singularity extends far beyond its immediate vicinity. It affects the geometry of space-time, creating a curvature that can be visualized as a deep well in a flat surface. Objects in orbit around a black hole, for instance, do not merely follow a circular path. They trace intricate spirals shaped by the invisible hand of gravity. As they approach the event horizon, they appear to slow down, their light redshifting as they struggle against the gravitational pull. Imagine observing this cosmic ballet, where the dance of celestial bodies is dictated by the unseen force of a singularity, a force that governs the very rhythm of the universe. The relationship between singularity and gravity is a profound one, steeped in the mysteries of general relativity. According to Einstein's theory, massive objects warp the fabric of space-time, and singularities represent the extreme end of this phenomenon. In essence, they are the ultimate manifestation of gravity's relentless grasp. Yet, as we explore deeper, we encounter a paradox. The very equations that describe gravity also lead to singularities, suggesting that our understanding of gravity is incomplete. This brings us to the intriguing notion of gravity at the quantum level. While general relativity elegantly describes the cosmos on a grand scale, the behaviors of particles at the quantum level remain enigmatic. The quest to reconcile these two realms has given rise to theories such as string theory and loop quantum gravity. In these frameworks, singularities may be reinterpreted as points of transition rather than destruction. What if, instead of obliterating everything in their vicinity, singularities act as gateways to alternate dimensions or realities? The possibilities are exhilarating, inviting us to contemplate a universe rich with potential beyond our current perception. As we immerse ourselves in these theories, we find ourselves standing at the frontier of human knowledge, peering into the abyss of the unknown. The exploration of singularities is not merely an academic exercise. It is a journey that reflects our innate curiosity and desire to understand our place in the cosmos. As Carl Sagan beautifully articulated, somewhere, something incredible is waiting to be known. This sentiment resonates deeply as we probe the depths of singularities, searching for answers that may illuminate the darkness. The quest to comprehend singularities also has profound implications for our understanding of time itself. In regions of extreme gravity, such as those found near a black hole, time behaves differently. As an observer approaches a singularity, the passage of time slows drastically compared to someone far from its gravitational influence. Imagine standing on the edge of a vast chasm, peering into its depths, where time stretches like a rubber band. This phenomenon, known as gravitational time dilation, raises questions about the nature of reality and our perception of existence. What does it mean for our lives, for our understanding of aging and mortality, if time can be manipulated in such dramatic ways? If we could harness the secrets of singularities, could we unlock the key to time travel? Theoretical physicists continue to explore these tantalizing possibilities, igniting our imaginations with visions of journeys through time and space. As we reflect on the singularity, we are reminded of the delicate balance between fascination and fear. It embodies the unknown, a reminder that the universe is replete with mysteries waiting to be unveiled. The gravitational pull of a singularity not only draws matter towards it, but also invites us to confront our own limitations. As we endeavor to make sense of this cosmic enigma, we acknowledge that every answer breeds further questions, a cycle of discovery that propels humanity forward. The exploration of singularities is a testament to our persistent quest for knowledge, an endeavor that transcends generations and cultures. As we gaze into the heavens, we are inspired by the brilliance of those who have come before us, whose insights have illuminated the path to understanding. The words of physicist Niels Bohr resonate profoundly. An expert is a person who has made all the mistakes that can be made in a very narrow field. Embracing this wisdom, we venture into the realm of singularities with humility, aware that each hypothesis and discovery is but a stepping stone towards greater enlightenment. In the heart of a black hole lies an invitation to transcend our earthly perceptions and embrace the grandeur of the cosmos. The singularity, with its infinite density and unfathomable depths, beckons us to consider the interconnectedness of all things. What if the singularity, with its enigmatic properties, holds the key to understanding not only black holes, but the very essence of existence? As we continue our exploration, let us remain open to the infinite possibilities that lie ahead, knowing that the journey into the depths of singularities is not merely a quest for knowledge, but a reflection of our deepest hopes and dreams as inhabitants of the universe. The mysteries of the singularity remind us that, even in the face of the unknown, the pursuit of understanding is a journey worth taking, one that may ultimately lead us to the very core of reality itself. As we stand at the precipice of understanding the singularity, we cannot ignore its profound influence on the very fabric of space-time. The interplay between gravity and the cosmos reveals a complex dance, where the warping of space-time creates a tapestry of phenomena that challenge our perceptions. In the following chapter, we will delve deeper into these gravitational effects, exploring how black holes not only distort the space around them, but also shape the experiences of those who venture close to their immense power. Prepare to journey further into the realms of time dilation and the ripples of gravitational waves as we unravel the intricate connections that bind our universe together. Chapter 4. Gravitational Effects, Space-Time Distortion. As we delve into the profound nature of gravity, we begin to understand its remarkable power to shape not just the physical world around us, but also the very fabric of time itself. Imagine for a moment a vast, serene expanse where time flows differently depending on the gravitational forces at play. This phenomenon, known as time dilation, reveals how gravity influences our perception of time. When we consider the effects of gravity, we often think of its force pulling objects toward one another, but gravity does much more than that. It bends the paths of light and warps the passage of time. The closer we are to a massive object, the slower time ticks, relative to someone far away from it. Albert Einstein, the architect of the theory of relativity, famously stated, "The only reason for time is so that everything doesn't happen at once." This notion of time, intertwined with gravity, presents a captivating interplay that invites us to ponder the nature of our existence. Now, let us turn our attention to one of the most intriguing manifestations of gravity: black holes. These cosmic giants possess such immense mass that they warp the space-time surrounding them like a heavy ball resting on a stretched sheet. Imagine this sheet as the very fabric of the universe, where the presence of a black hole creates a deep well, pulling everything around it closer. As we approach a black hole, we experience a profound distortion of space and time. The gravitational pull becomes so intense that it alters our perception in unimaginable ways. Picture a traveler nearing the event horizon, the point of no return. For them, time may appear to slow dramatically, while an observer, watching from a safe distance, would see time pass for the traveler at a sluggish pace. This relativistic phenomenon illustrates how gravity can bend our experiences, revealing the deep connection between time and space. Consider the vivid scenario of two twin siblings, one remaining on Earth and the other embarking on a journey close to a black hole. Upon the traveling twins' return, they discover that years have passed for their Earth-bound sibling, while only a short while has elapsed for them. This difference in aging, a direct result of time dilation, showcases the profound relationship between gravity and time perception. The effects of gravity extend beyond mere time dilation. They also influence the behavior of nearby objects. When stars and planets orbit a black hole, they are not just moving through space, they are also dancing through warped time. As they spiral closer, their paths become increasingly distorted, creating an intricate ballet of celestial bodies caught in the gravitational grip of the black hole. This gravitational influence is further amplified by the phenomenon of tidal forces, where the difference in gravity experienced by objects at varying distances from the black hole can lead to spectacular displays of cosmic destruction. Imagine a star being pulled apart, stretched like spaghetti, as it ventures too close to the event horizon. This spaghettification, as it is aptly named, is a stark reminder of the power wielded by black holes and the intricate interplay of gravity and time. As we contemplate these extraordinary gravitational effects, we are led to one of the most fascinating predictions of modern physics: gravitational waves. These ripples through space-time, caused by the acceleration of massive objects, were first predicted by Einstein in his general theory of relativity. Imagine throwing a stone into a calm pond, watching the waves radiate outward. In the cosmic realm, when two black holes collide, they create waves that ripple through the fabric of space-time, carrying with them information about their origins and the dynamics of their interaction. The first detection of gravitational waves in 2015 marked a monumental milestone in our understanding of the universe. Researchers celebrated this achievement, as it not only confirmed a key prediction of relativity, but also opened a new window into the cosmos. As physicist Kip Thorne, one of the pioneers in this field, remarked, "Gravitational waves are like the sound of the universe. They tell us about the most violent events in the cosmos." Through the lens of gravitational waves, we gain insights into black holes, neutron stars, and even the origins of the universe itself. Each wave carries a story, a piece of cosmic history that reveals the dynamic and often violent nature of the universe. Imagine listening to these waves, each fluctuation a whisper from the cosmos, sharing tales of creation and destruction, of collisions and births. It evokes a sense of connection, reminding us that we are part of something far grander than ourselves, woven into the very fabric of the universe. As we explore the gravitational effects on space-time distortion, we begin to appreciate how deeply intertwined our reality is with these cosmic phenomena. The gentle pull of gravity shapes the very essence of our existence, influencing not just the paths of celestial bodies, but also the flow of time itself. What if we could harness this knowledge, using it to glimpse the mysteries of the universe? In this realm of gravitational effects, we find ourselves standing at the precipice of understanding, ready to embark on a journey through the intricate and captivating universe that surrounds us. Each discovery, each revelation, invites us to look deeper into the nature of reality and our place within it, reminding us that the universe is a wondrous expanse, filled with secrets waiting to be uncovered. As we delve deeper into the realm of gravitational effects, we encounter the intriguing phenomenon of time dilation, a concept that reshapes our understanding of time itself. Imagine a clock ticking steadily in a serene valley, while another clock, suspended in the gravitational embrace of a massive object, ticks at a different pace. For those in the valley, time flows like a gentle stream, while for those near the massive object, it appears to crawl, a mesmerizing dance of seconds stretching into eternity. This is no mere theoretical abstraction. It is a reality born out of Einstein's theory of relativity. Gravity, it turns out, has the power to bend time, creating a ripple effect that alters our perception of its passage. As renowned physicist Albert Einstein once stated, "Time and space are modes by which we think, and not conditions in which we live." This profound insight encourages us to envision time not as a rigid sequence of moments, but as a fluid entity, shaped by the gravitational forces at play around us. Consider the example of GPS satellites orbiting Earth, positioned high above the planet's surface. These satellites experience a weaker gravitational force compared to those of us on the ground. As a result, the clocks on these satellites tick slightly faster than those on Earth. If left uncorrected, this difference would cause navigational errors to accumulate, leading to significant deviations over time. It is a remarkable reminder of how gravity intricately weaves itself into the fabric of our daily lives, influencing even the most mundane activities. Now imagine standing on the edge of a black hole, where gravity reaches its zenith. As we approach this cosmic giant, the effects of time dilation become extraordinarily pronounced. For an observer hovering at a safe distance, time appears to slow down for anything falling toward the black hole. This creates a surreal spectacle. Watching an object spiral into the abyss feels like witnessing a slow-motion ballet, as seconds stretch into what seems like hours. This phenomenon invites us to ponder, what would it feel like to experience time in such a way? How would our understanding of life and existence shift if we could perceive time as a malleable essence, shaped by the forces around us? As we explore the gravitational effects on nearby objects, the interplay between gravity and motion reveals a captivating narrative. Picture the celestial bodies in the vast expanse of space, each influenced by the gravitational pull of its neighbors. Planets dance around stars, their paths choreographed by the invisible threads of gravity that bind them together. A planet's orbit is not merely a result of its distance to the star. It is a beautiful symphony of forces, harmonizing gravitational attraction with the planet's momentum, creating an intricate balance that allows life to flourish on worlds like our own. Gravity also plays a pivotal role in the formation of galaxies. As gas and dust coalesce under the weight of gravity, they give birth to stars, which in turn forge the elements that form planets and life. This cosmic cycle exemplifies the profound truth that gravity is not just a force of attraction. It is a creative force, shaping the universe in ways both subtle and grand. Have you ever wondered how the simple act of a star's birth can ripple across the cosmos, influencing countless other celestial bodies? It is a testament to the interconnected nature of the universe, where every action reverberates in a grand cosmic symphony. Yet, black holes stand as the most striking manifestations of gravitational distortion. Their immense gravitational pull warps the very fabric of space-time around them. As matter spirals into a black hole, it encounters a gravitational gradient that stretches and compresses, creating a phenomenon known as spaghettification. Imagine a strand of spaghetti pulled taut, elongated by a powerful force. This dramatic effect is a vivid reminder of the extremes of gravity, and it captivates our imagination, prompting reflections on the nature of existence itself. The universe, it seems, is not just a collection of stars and planets. It is a theater of spectacular events, each driven by the relentless pull of gravity. The theoretical predictions of gravitational waves further illuminate the dynamic nature of the universe. These ripples in space-time, generated by the acceleration of massive objects, bring us whispers from the farthest reaches of the cosmos. When two black holes collide, their merger sends out waves that travel across the universe, carrying the story of their violent union. As these gravitational waves pass through space, they distort the fabric of reality, enabling scientists to detect events that occurred billions of years ago. The beauty of gravitational waves lies not only in their significance for astrophysics, but also in the profound questions they raise. What do these waves reveal about the nature of the universe? How do they connect us to distant epochs, allowing us to witness the birth and death of stars? Each wave holds the potential to unlock mysteries, encouraging us to explore deeper, to seek understanding in the face of the unknown. As we ponder the implications of these discoveries, we are reminded of the words of physicist Neil deGrasse Tyson. The universe is under no obligation to make sense to you. This humbling truth invites us to embrace the wonder of the cosmos, to approach it with curiosity and awe. The gravitational effects we observe are but a glimpse into the complexities of existence, inviting us to reflect on our own place within this vast tapestry. What if we could harness our understanding of gravity and time? What new realms of exploration might await us? The journey through gravitational effects and space-time distortion is not merely an academic pursuit. It is a profound voyage into the heart of reality, where each revelation inspires us to dream bigger and reach for the stars. In this unfolding story of the universe, we are both spectators and participants, woven into the intricate narrative of existence, forever captivated by the mysteries that lie ahead. As we marvel at the intricate dance of gravitational waves and the enigmatic nature of black holes, we find ourselves standing at the precipice of profound questions about existence and survival against the backdrop of cosmic extremes. What if, amidst the chaos of spaghettification and the fabric of space-time unraveling, there lay a hidden realm where life could endure? This tantalizing possibility invites us to explore the theoretical constructs of habitability within a black hole, an idea that challenges the very limits of our understanding. In the next chapter, we will delve into the astonishing hypothesis of living inside a black hole, examining the conditions that might allow life to flourish in such an extraordinary environment. Together, we will navigate the paradoxes and challenges that come with this audacious concept, igniting our imagination as we seek to uncover what lies beyond the event horizon. Chapter 5. Theoretical Living Inside a Black Hole. Imagine, if you will, the vast darkness of a black hole, a cosmic abyss that swallows light and distorts the very fabric of reality. Beyond this horizon lies a realm of theoretical possibility, a place where the rules of existence as we know them may bend and twist. What happens to matter that crosses this threshold? Once an object crosses the event horizon, it is irrevocably drawn into the singularity, where the gravitational forces are so extreme that they challenge our understanding of physics. Yet, what if we entertain the notion that life could somehow survive within this strange domain? Could there exist a sanctuary amidst the chaos, a theoretical construct that allows for life to thrive in such an unfathomable place? The hypothesis of surviving within a black hole begins with the idea of a habitable zone, a concept usually reserved for distant exoplanets orbiting stars. In the heart of a black hole, this zone would be defined not by distance from a star, but by the delicate balance of gravitational forces and exotic conditions. Could life adapt to thrive in a realm where the laws of physics are profoundly altered? Conditions necessary for life, as we understand it, include the presence of liquid water, a stable atmosphere, and an energy source. In the depths of a black hole, these requirements take on new meanings. Picture a world where gravitational tidal forces create pockets of immense pressure and heat, perhaps even fostering chemical reactions that could mimic the primordial soup of early Earth. Some scientists have speculated that if a structure could remain intact, life might find a way to exist, even in the extreme conditions of a black hole's interior. One captivating theory suggests that if a massive black hole were to spin rapidly, it might create a disk of matter around it. This accretion disk, filled with gas and dust, could generate heat and energy, much like the sun does for Earth. Within this swirling maelstrom, sheltered from the crushing grasp of the singularity, life could potentially find a niche. As physicist Kip Thorne once said, "The universe is not only queerer than we suppose, but queerer than we can suppose." This invites us to wonder, what forms could life take in such an environment? However, the challenges and paradoxes of living inside a black hole are daunting. The immense gravitational pull would create a world of extremes, where time itself behaves differently. Imagine experiencing time at a different rate than those outside the black hole. A moment for you could stretch into an eternity for someone far away. This phenomenon, known as time dilation, could lead to a reality where life evolves at a pace that seems surreal to an outsider. Moreover, the very nature of matter itself raises profound questions. What happens to organic compounds and biological structures under such intense gravitational forces? Are they stretched, compressed, or even altered at a molecular level? The idea of spaghettification, the stretching of objects into thin strands as they approach the black hole, looms large in our imaginations. In such a world, the essence of life might transform, adapting in ways we cannot currently comprehend. Theoretical physicists like Stephen Hawking have pondered these possibilities and proposed models that stretch the imagination. Hawking famously remarked, "If black holes aren't really black, they will emit radiation." This notion hints at the potential for energy sources within a black hole's accretion disk, suggesting that life could harness energy in ways that defy our current understanding. Yet amid these tantalizing possibilities, we must confront the paradoxes that arise. How can life persist in a place where the fundamental rules of existence appear to break down? Is it even possible for consciousness to exist within such a realm, where the very fabric of space and time is in constant flux? These questions linger like echoes in the void, urging us to explore the boundaries of our understanding. As we contemplate the theoretical existence of life within a black hole, we are drawn to the idea of resilience and adaptation. Life, as we know it, has evolved to thrive in environments that seem inhospitable, from the icy depths of the ocean to the boiling vents of volcanic landscapes. Could it be that in the heart of a black hole, life finds a new canvas upon which to paint its story? Imagine a world where the laws of physics create a unique ecosystem, one that is alien yet familiar. The scientists among us dream of such possibilities, driven by an insatiable curiosity. The very thought of life taking root in such an extraordinary environment challenges our perceptions and invites us to rethink the limits of existence. Thus, we stand on the brink of a cosmic mystery, a place where science and imagination intertwine. The fate of matter beyond the horizon remains an enigma, but the quest to understand it fuels our exploration of the universe. As we peer into the darkness of black holes, we are reminded that the cosmos holds secrets yet to be revealed, waiting patiently for those bold enough to seek them. What happens to matter that crosses the event horizon? This is a question that beckons the curious mind, inviting us to delve deeper into the mysteries of a black hole's interior. Beyond this boundary, the gravitational pull becomes so intense that not even light can escape its grasp. As matter spirals into this abyss, it succumbs to a phenomenon known as spaghettification, where the immense gravitational gradient stretches and compresses objects into elongated shapes akin to spaghetti. Imagine the fate of a star, As it approaches this menacing edge, the side closest to the black hole experiences a stronger gravitational pull than the side facing away. This differential force, coupled with the immense pressures at play, leads to the disintegration of the star. The process serves as a reminder of how black holes can transform celestial bodies into a cosmic ballet of destruction and rebirth, reshaping matter into new forms. But what if we turn our attention to the idea of surviving within this cosmic crucible? The notion of life inside a black hole challenges our understanding of existence itself. Could there be regions, possibly near the black hole's singularity, where the conditions align to support a form of life? Theoretical constructs suggest that if one could harness the extreme energies and gravitational forces, a habitable zone might emerge, albeit vastly different from the environments we know. Envision a landscape where space-time curves around you, creating a surreal panorama of distorted light and gravity. It is a world where time flows at a different rate, and distances stretch and compress in a manner that eludes our comprehension. Could life adapt to such an environment? As physicist Albert Einstein once said, "The most incomprehensible thing about the world is that it is comprehensible." Perhaps through the lens of imagination and scientific inquiry, we can begin to envision how life could emerge in such extraordinary circumstances. The conditions necessary for life to thrive often include the presence of water, a stable temperature range, and an energy source. In the extreme environment within a black hole, these factors would need to be redefined. Could we envision liquid water existing in the form of exotic states, perhaps suspended in a balance between immense pressures and temperatures? The potential for life utilizing alternative biochemical pathways, perhaps relying on processes unknown to us, invites us to expand our definitions of biology. Imagine organisms thriving on energy derived from gravitational forces or harnessing the intense radiation emitted from the vicinity of the singularity. These hypothetical beings might possess mechanisms to shield themselves from the relentless energies that pervade their surroundings. The resilience of life in the face of adversity has been observed throughout our planet, from extremophiles in harsh volcanic vents to tardigrades enduring the vacuum of space. Might there exist a similarly tenacious life form within the folds of a black hole? Yet the concept of living in such a realm is not without its challenges. The paradoxes of existence within a black hole raise questions that stretch the limits of our understanding. If life were to exist beyond the event horizon, what would happen to the information that defines it? According to the laws of quantum mechanics, information cannot be destroyed. Yet the very nature of a black hole suggests that anything crossing the event horizon may be lost to the universe. Stephen Hawking once posited, "Black holes ain't as black as they are painted." His contemplation of Hawking radiation opens a window into the complexities of information and existence, suggesting that perhaps, in ways we do not yet comprehend, life may find pathways to persist. The challenges of energy acquisition in such an environment are formidable. Traditional sources of energy, such as sunlight or chemical reactions, become irrelevant in the overwhelming darkness. Instead, one might imagine organisms able to tap into the gravitational energy, converting it into usable forms. This concept challenges our conventional views of energy dynamics, inviting new possibilities for understanding life itself. Furthermore, the journey to comprehend life within a black hole is also a journey into the nature of time. As one moves closer to the singularity, time behaves in ways that defy our everyday experiences. The phenomenon of time dilation means that for someone falling into a black hole, time could stretch and bend, offering a surreal experience of existence. How would this altered perception of time impact consciousness? Would awareness persist in a state that transcends the linear progression of time as we know it? As we reflect on these questions, we find ourselves at the intersection of science and philosophy. The implications of existing within a black hole might not only redefine our understanding of biology, but also challenge our perceptions of reality itself. Perhaps existence is more fluid than we have imagined, allowing for a spectrum of life that stretches beyond our conventional frameworks. The challenges and paradoxes of living inside a black hole are profound. It forces us to confront the limitations of our knowledge and the boundaries of our imagination. As we ponder the nature of this cosmic enigma, we cannot help but wonder about the implications for our understanding of the universe itself. What mysteries lie hidden in the abyss, waiting for the minds willing to explore? In the face of these questions, we are reminded that curiosity is an intrinsic part of the human experience. Theoretical explorations into the nature of life within a black hole encourage us to embrace the unknown, to dream of possibilities that may seem unattainable. The cosmos invites us to look beyond the familiar and to seek answers in the realms of imagination and science. As we venture into this uncharted territory, we expand our understanding of what it means to exist, to adapt, and to thrive against all odds. The universe, with all its wonders and mysteries, continues to call forth our exploration. It stirs within us a sense of wonder, urging us to ask not only what lies beyond the horizon, but also what lies within the very fabric of existence itself. Each question we pose opens a door to new realms of thought, inviting us to step into the unknown and embrace the beauty of discovery. As we stand at the precipice of understanding, the exploration of life within a black hole compels us to reconsider not only the nature of existence, but also the very fabric of reality itself. The questions raised about time, consciousness, and the fluidity of life echo into the vastness of the cosmos, suggesting that our universe may be just one of many. This notion invites us to delve deeper into the intriguing concept of the multiverse, where black holes could serve as gateways to alternate realities. In the next chapter, we will unravel the connections between these cosmic phenomena and the tantalizing possibility of parallel universes, exploring how they reshape our understanding of life and existence in ways we have yet to fully comprehend. The journey through these alternate realms promises to expand our horizons, challenging us to envision the unimaginable. Chapter 6: Alternate Realities, the Multiverse Theory. Imagine a vast expanse, a realm where the boundaries of reality blur and intertwine, leading to the fascinating concept of the multiverse. At its core, the multiverse theory suggests that our universe is just one of many, each potentially harboring its own peculiar laws of physics, properties, and realities. Within this cosmic playground, black holes emerge as enigmatic portals, whispering secrets about the nature of existence itself. As we delve deeper into the relationship between black holes and alternate universes, we are invited to ponder a curious question. Could these cosmic giants serve as gateways to entirely different realms? Picture a black hole, a swirling vortex of darkness, its event horizon a threshold to the unknown. Some theorists propose that when matter crosses this boundary, it may not simply be consumed, but instead could be transported to another universe, a parallel reality where the rules of our own cosmos no longer apply. In the heart of these black holes, could there exist a unique environment that allows for the emergence of life forms unlike anything we have ever imagined? The conditions may seem inhospitable, yet the universe is famously unpredictable. As we explore the implications of parallel realities for life, we discover the potential for extraordinary adaptations. Life as we know it is remarkably resilient. It flourishes in the most extreme conditions on Earth, from the crushing depths of the ocean to the blistering heat of volcanic vents. Just as extremophiles thrive where most could not survive, what if beings within a black hole adapted to its peculiarities? Consider the words of physicist Brian Greene. The universe is a strange place, and we've only just begun to scratch the surface of understanding it. In this light, the multiverse becomes an extension of our quest to comprehend the cosmos. If black holes act as conduits to alternate realities, it opens up a realm of possibilities for life forms that could exist in those dimensions. They might harness energy in ways we cannot fathom, relying on gravitational waves or quantum fluctuations to thrive. Theoretical frameworks supporting the multiverse concept are diverse, yet they converge on the idea that our universe may be just one bubble in a grand cosmic foam. String theory, for instance, posits that fundamental particles are not point-like but rather tiny vibrating strings. This framework suggests a multitude of dimensions beyond our perception, where black holes could connect these hidden realms. Imagine standing at the edge of a vast ocean of universes, each wave representing a different reality. In some, the laws of nature might allow for sentient beings that communicate through vibrations instead of sound, while in others, time itself could flow backward. These alternate realities challenge our understanding of existence and invite us to consider the very nature of consciousness. What does it mean to be alive in a universe where every possibility is played out in parallel? As we reflect on the implications of such a multiverse, we encounter the thoughts of physicist Max Tegmark, who stated, "The multiverse is not a theory, it's a necessary consequence of our understanding of quantum mechanics." If we accept that every quantum event branches into multiple outcomes, it follows that black holes could serve as a bridge, linking these diverging realities. The notion of hypothetical life forms thriving in the interiors of black holes beckons us to explore their potential characteristics. These beings may possess forms and abilities tailored to their unique environments, perhaps utilizing gravitational forces to navigate their surroundings or manipulating energy in ways that seem magical to us. Could they harness the intense gravitational pull to create energy sources, or perhaps they have evolved to withstand extreme temperature variations? In contemplating these possibilities, one cannot help but wonder, how would such life forms perceive their existence? Would their understanding of reality differ from ours? The mysteries of consciousness and perception become ever more intricate in this cosmic tapestry. As we turn our gaze back to the scientific frameworks that support the multiverse theory, we find that they weave together elements of quantum physics and cosmology. The idea that black holes could be gateways to alternate universes is supported by theories of cosmic inflation, suggesting that our universe underwent a rapid expansion after the Big Bang, creating a diverse landscape of realities. The implications of these connections extend beyond mere speculation. They challenge our understanding of life itself, encouraging us to redefine what it means to exist. Could life emerge in forms we cannot yet conceive, thriving in the gravitational embrace of a black hole? Would these beings develop a consciousness that transcends our understanding, allowing them to perceive dimensions beyond our reach? As we explore the vast potential of the multiverse, we must also acknowledge the limitations of our current understanding. Theoretical physicist Stephen Hawking once said, "The only black hole we can be sure of is the one we see in the sky." While we can speculate on the existence of alternate realities and the life forms that may inhabit them, the challenge of proving such theories persists. Yet it is this very challenge that fuels the fire of scientific inquiry, driving us to explore the unknown. In our journey through the cosmos, we are reminded of the interconnectedness of all things. The fabric of reality, woven with threads of possibility, invites us to wonder about the nature of existence. As we contemplate the mysteries of black holes and the multiverse, we are left with a profound sense of awe and curiosity. What lies beyond the event horizon? Are there worlds waiting to be discovered, each with its own story to tell? The answers remain tantalizingly out of reach, yet the exploration itself is a testament to our unyielding quest for knowledge. In this pursuit, we find not only the potential for understanding the universe, but also a deeper connection to the essence of life itself. As we continue to ponder these intriguing ideas, let us embrace the beauty of uncertainty. The multiverse beckons us to explore the infinite possibilities that lie within and beyond the realms we know. In doing so, we may uncover not only the secrets of black holes, but also the very nature of reality itself. As we delve deeper into the multiverse theory, the notion of alternate realities begins to weave itself into the very essence of our understanding of black holes. Imagine, if you will, a swirling vortex of darkness, a black hole acting as a portal to universes yet unimagined. Could it be that these cosmic giants serve as gateways to realms where the laws of physics play by entirely different rules? Theoretical physicists have long speculated on this connection, suggesting that black holes might not only devour stars and matter, but could also expel them into other dimensions. The idea of parallel universes is not merely a fanciful notion. It is rooted in complex theories that challenge our perception of reality. Quantum mechanics introduces us to the concept of superposition, where particles exist in multiple states simultaneously. This principle has led to the hypothesis that every decision, every moment, branches off into a new universe, creating an infinite array of realities. The physicist Hugh Everett III proposed this many-worlds interpretation in the 1950s, suggesting that every quantum event spawns a new universe, each containing its own version of reality. As we ponder this, we might ask ourselves, what choices have led us to the lives we live today? How many alternate versions of ourselves exist in these parallel realms? Envision a universe where the conditions for life differ vastly from our own. In some realities, perhaps entire ecosystems thrive in environments we would deem inhospitable. Could there be life forms that have adapted to the crushing gravity and intense radiation of a black hole's vicinity? These hypothetical beings might harness energy from their surroundings in ways that defy our current understanding of biology. The renowned astrophysicist Brian Cox speculated, if you could survive in a black hole, what would you look like? How would you exist? These questions inspire a sense of wonder, urging us to expand our horizons and embrace the fantastic diversity that the cosmos may offer. The implications of such parallel realities extend far beyond mere speculation. If black holes are indeed conduits to alternate universes, what does this mean for our understanding of existence? Imagine a world where time moves differently, where the past and future intertwine in ways we cannot comprehend. The theory suggests that the very act of observation can alter the outcome of events. What if, in another reality, we made a different choice, leading to a cascade of consequences that shaped an entirely different universe? Each decision, a delicate thread in the vast tapestry of existence, could resonate across dimensions, creating echoes that ripple through time and space. As we seek to understand these complex ideas, we must also consider the theoretical frameworks that support the multiverse concept. String theory, for instance, posits that the fundamental building blocks of the universe are tiny, vibrating strings existing in multiple dimensions. This theory not only attempts to unify gravity with quantum mechanics, but also suggests the existence of additional dimensions that could harbor alternate realities. These unseen realms might be just beyond our perception, waiting to be discovered by those daring enough to venture into the unknown. The interplay between black holes and the multiverse invites us to reflect on the nature of reality itself. Are we merely observers, or do our thoughts and actions weave the very fabric of existence? Philosopher and physicist David Deutsch expressed this sentiment beautifully when he stated, "We are not just observers of the universe, we are participants in its creation." This perspective urges us to consider our role in the grand narrative of the cosmos, fostering a deeper connection to the mysteries that surround us. As we explore the potential for life in alternate realities, we cannot ignore the challenges posed by extreme environments. The conditions near a black hole are like none we have ever encountered. Intense gravitational forces, extreme temperatures, and radiation levels that would obliterate conventional life as we know it. Yet, if we allow our imaginations to roam free, we might envision life forms that thrive in such conditions, perhaps utilizing bioluminescence to communicate or developing unique biochemical processes to withstand the onslaught of radiation. What if these entities possess forms of intelligence that differ fundamentally from our own? How would they perceive their reality, and what kind of societies might they build? The possibilities are as vast as the cosmos itself, inviting us to ponder the diversity of life that could flourish beyond our comprehension. Our quest to bridge the gap between black holes and the multiverse is not merely an academic pursuit. It is a journey steeped in curiosity and wonder. Each discovery unveils new layers of complexity, challenging our understanding and inviting us to rethink our place in the universe. As physicist Max Tegmark eloquently stated, the universe is not just out there, it is also within us. In this embrace of the unknown, we may find solace, for it is the very act of discovery that enriches our lives. The mysteries of black holes and the multiverse call to us, urging us to explore and to dream. As we contemplate the vastness of existence, we are reminded that the answers may lie hidden within the shadows, waiting patiently for us to uncover their secrets. Each question leads to new avenues of inquiry, propelling us forward into the depths of the cosmos, where the line between reality and imagination blurs, and the adventure of understanding unfolds. As we stand on the precipice of understanding, the allure of black holes beckons us deeper into the cosmic abyss, where our curiosity meets the harsh realities of exploration. The mysteries we've unearthed thus far not only provoke our imagination, but also set the stage for the next phase of our journey. With current scientific methods and theoretical approaches at our disposal, we are now poised to probe the very interiors of these enigmatic giants. Yet, as we prepare to venture into these extreme environments, we must confront the formidable challenges that lie ahead in our quest for knowledge. Join us as we delve into the intricate dance between ambition and adversity in our exploration of black hole interiors, where the unknown awaits with both peril and promise. Chapter 7. Exploring Black Hole Interiors, Scientific Probes. As we embark on a journey through the enigmatic realms of black holes, we find ourselves drawn into the mysterious pathways of cosmic rays and their remarkable journeys through these celestial giants. Cosmic rays, the high-energy particles that rain down upon our atmosphere from the depths of space, are primarily protons, but they also include heavier atomic nuclei and electrons. Their origins are as varied as the universe itself, with some stemming from explosive events like supernovae or the violent dance of neutron stars. Imagine these particles traveling through the cosmos, propelled by forces we are only beginning to understand. When these cosmic rays approach a black hole, they begin to interact with the extreme gravitational pull that warps the very fabric of space-time. Some may spiral towards the event horizon, while others may be deflected, their paths altered as they experience gravitational lensing. This act of bending light and particles creates a vivid tapestry of cosmic drama, one that scientists strive to comprehend. Current methods for studying black holes rely heavily on indirect observations. Astronomers utilize advanced telescopes equipped with specialized sensors, capturing the light emitted from accretion disks, the swirling material spiraling into a black hole. These disks are often composed of gas and dust, heated to extreme temperatures as they are drawn inexorably towards the singularity. The emitted X-rays and gamma rays provide valuable information about the black hole's mass and spin, as well as the dynamics at play within its surroundings. Yet the universe is vast and complex, and the challenge of studying black holes deepens when one considers the need to probe their interiors. Theoretical approaches to explore these hidden realms often involve intricate mathematics and creative thought experiments. Some scientists propose using advanced simulations to model the conditions within a black hole, offering insights into how gravity and quantum mechanics might intertwine in these extreme environments. Imagine what it would be like to send a probe into a black hole, equipped with technology far beyond our current capabilities. What instruments would it need? What data could it collect before succumbing to the gravitational forces? These are the questions that fuel the imagination of astrophysicists and engineers alike. Some theorists suggest using hypothetical constructs, such as wormholes or quantum entanglement, as pathways to access the secrets hidden within a black hole's core. However, the challenges of data collection in these extreme environments are formidable. The immense gravitational pull of a black hole creates a hostile landscape, where traditional sensors would likely be crushed long before they could transmit any meaningful information. The concept of spaghettification, where objects are elongated and compressed as they approach the event horizon, serves as a reminder of the perilous conditions that prevail. As physicist Kip Thorne once said, "Black holes are where God divided by zero." This statement serves not only as a playful quip, but also reflects the insurmountable obstacles that scientists face when attempting to gather data from such a chaotic environment. Yet hope remains on the horizon. Future technologies may soon empower us to delve deeper into the mysteries of black holes than ever before. One such advancement could be the development of quantum sensors, which promise to enhance our ability to detect faint signals and gravitational waves emanating from these cosmic entities. These sensors could potentially revolutionize our understanding, allowing for more precise measurements of gravitational effects and even the exploration of information paradoxes that arise from the interaction of matter and black holes. As we ponder the future, we can envision spacecraft equipped with advanced AI systems capable of analyzing data in real time, offering insights while navigating the extreme conditions surrounding a black hole. Imagine a fleet of probes deployed to study the accretion disks, mapping their compositions and behaviors, all while transmitting findings back to Earth. In this ever-evolving landscape of black hole research, we stand on the cusp of a new era, one where the unknown may soon become known. The journey through the heart of darkness continues to captivate our collective imagination, drawing us ever closer to the answers we seek within the cosmic void. The exploration of black hole interiors beckons with the promise of discovery, inviting us to ponder the very nature of existence itself. As we venture into the realm of cosmic rays, we find ourselves confronting one of the universe's most enigmatic phenomena. Cosmic rays are high-energy particles that travel through space, often arriving at our planet with extraordinary velocities. Imagine these particles as messengers from the farthest reaches of the cosmos, carrying the stories of their creation and journey across the universe. Most cosmic rays originate from supernova explosions or other high-energy astrophysical events. But what happens when they encounter the gravitational embrace of a black hole? When cosmic rays approach a black hole, they experience an environment vastly different from the one we know on Earth. The immense gravitational field can accelerate them to unfathomable speeds, sometimes pushing them beyond the threshold of light speed, at least in terms of their relative motion through space. As they spiral into the black hole's grasp, these particles can be subjected to extreme tidal forces that may strip away their very essence, altering their trajectories and energies. The energy levels of these cosmic rays can reveal crucial information about their origins and the processes at play in their journey, acting as a conduit to the hidden depths of black hole interiors. Dr. James Peebles, a Nobel Prize-winning physicist, remarked, "The universe is a mathematics we cannot comprehend." This sentiment resonates deeply when we consider the mathematics behind cosmic rays and black holes. The complex equations governing these interactions challenge our understanding and beckon us to explore further. How do these cosmic messengers tell us about the very nature of black holes? Through current methods of studying black holes and cosmic rays, scientists utilize a combination of observational astronomy and theoretical modeling. Instruments such as the Large Hadron Collider and the upcoming space observatories are designed to capture the elusive signatures of cosmic rays as they interact with black holes. These observations become puzzles, each piece representing a fragment of knowledge that, when assembled, may unlock the secrets of the universe. Yet, the challenges of data collection in such extreme environments cannot be overstated. The area surrounding black holes is not merely a vacuum. It is a cauldron of radiation and violent forces. Instruments must be resilient, capable of withstanding conditions that would obliterate the delicate sensors we currently use. Imagine designing a device that must endure not just the gravitational pull of a black hole, but also the intense radiation emitted from the accretion disks, swirling around its event horizon. Theoretical approaches to exploring black hole interiors offer tantalizing possibilities. One of the most intriguing concepts is that of gravitational lensing, where the light from distant stars is bent and distorted as it passes near a black hole. This natural phenomenon can be harnessed to glean insights into the mass and spin of black holes, allowing scientists to infer the properties of their interiors without direct observation. As the light travels through warped space-time, it reveals hidden dimensions of black holes, drawing the observer into a dance of light and gravity. Imagine peering through a cosmic lens, where the very fabric of reality bends to reveal glimpses of the unseen. What if we could visualize the swirling mass of a black hole, the hints of matter falling into its depths? This visualization is not merely a fantasy, but rather an aspiration grounded in the science of today. It compels us to consider the potential of future technologies, such as advanced simulations and AI-driven models, which may allow us to predict the behavior of matter and energy in black hole environments with unprecedented accuracy. As we ponder these advancements, we are reminded of the profound complexity of black hole interiors. The theories surrounding them often intertwine with concepts from quantum physics, challenging our classical understandings. The research of physicist Brian Greene illustrates this beautifully when he states, "The universe is a symphony of strings, and the vibrations of those strings are what create the particles of matter." His work suggests that the very building blocks of the universe may be influenced by the mysterious forces at play within black holes. The exploration of black hole interiors is fraught with challenges, yet it is this very difficulty that fuels our desire to understand. The extreme environments surrounding black holes can create conditions where traditional physics breaks down, leading to paradoxes that intrigue scientists and philosophers alike. How do we reconcile the laws of physics with the phenomena observed in such regions? This question lingers, inviting us to delve deeper into the mysteries of the universe. As we look to the future, we can envision a time when technology allows us to probe these cosmic enigmas in ways we can only dream of today. The development of next-generation telescopes, capable of capturing high-resolution images of black hole accretion disks, could provide new insights into their behavior and structure. Coupled with advancements in computational power, simulations may illuminate the intricate dynamics at play within these cosmic giants, revealing the hidden symphony of matter and energy. The journey into the heart of black holes is not merely an academic pursuit, it is a quest for understanding that transcends the boundaries of human knowledge. It challenges us to confront the fundamental questions of existence, inviting us to explore the intersections of space, time, and the very fabric of reality. Each discovery brings with it the potential for new questions, new avenues of inquiry, and new horizons to explore. As we navigate these profound mysteries, we must also consider the ethical implications of our explorations. How does our quest for knowledge impact our understanding of the universe and ourselves? The pursuit of knowledge is a powerful force, one that can drive us to innovate and explore, but it also carries with it a responsibility to tread thoughtfully in the cosmic landscape. The allure of black holes lies not only in their scientific intrigue, but also in their ability to inspire wonder. They are cosmic beacons, inviting us to ponder our place in the universe and the nature of existence itself. The journey through the heart of darkness holds the promise of revealing truths that may redefine our understanding of reality. In the quiet moments of contemplation, we may find solace in the vastness of the cosmos. The stars twinkling above serve as a reminder of the mysteries yet to be unraveled. Each black hole, a silent sentinel of the universe, awaits the day when we may pierce its shrouded depths and emerge with a greater understanding of the cosmos and our own existence. The exploration of black hole interiors is an expedition not just through space, but through the very essence of what it means to be alive in this magnificent universe. As we stand on the precipice of understanding, the exploration of black hole interiors beckons us to consider not only the vastness of space, but also the intricate dance of quantum mechanics that governs the universe at its most fundamental level. The mysteries we have unraveled thus far are but the beginning, as they lead us to the tantalizing intersection of black holes and quantum physics, a realm where the laws of the macrocosmos collide with the peculiarities of the micro. It is here that concepts like Hawking radiation emerge, challenging our perceptions and inviting us to grapple with the profound implications of the information paradox. As we turn the page, we embark on a journey to bridge the gap between these two realms, seeking a unified theory that might illuminate the dark corners of our understanding and reshape our view of reality itself. Chapter 8. Black Holes and Quantum Physics, Bridging the Gap. Black holes, those enigmatic giants of the cosmos, play a crucial role in the universe's evolution. From their formation within the hearts of dying stars to their gravitational influence on surrounding celestial bodies, they are fundamental to our understanding of cosmic dynamics. They serve as cosmic vacuum cleaners, drawing in gas, dust, and even stars, shaping the very architecture of galaxies. Imagine the swirling arms of a galaxy, its stars and gas held in delicate balance, all under the watchful eye of a supermassive black hole at its center. As gas spirals inward, it heats up dramatically, emitting vast amounts of energy that light up the darkness, creating active galactic nuclei that can be observed across billions of light years. As we delve deeper into the cosmos, we encounter the fascinating intersection of black holes and quantum mechanics. This realm is where the familiar laws of gravity collide with the principles of the quantum world. Here, particles behave unpredictably, existing in superpositions of states and entangled across vast distances. The marriage of these two domains invites us to ponder the fundamental nature of reality itself. How do these seemingly disparate realms coexist? The answer lies in the ongoing quest to bridge the gap between general relativity, which governs the vastness of space and time, and quantum mechanics, which describes the behavior of the infinitesimally small. One of the most groundbreaking contributions to this conversation comes from the brilliant mind of Stephen Hawking. He proposed the concept of Hawking radiation, a form of thermal radiation that black holes emit due to quantum effects near their event horizons. This phenomenon suggests that black holes are not entirely black. They can lose mass and energy over time, eventually evaporating into nothingness. Imagine a black hole gradually shedding its weight, a cosmic light flickering in the vast dark. Hawking famously remarked, "Black holes ain't as black as they are painted." This revelation reshapes our understanding of these celestial giants, transforming them from eternal prisons of matter to dynamic entities capable of change. The implications of Hawking radiation ripple through the fabric of theoretical physics, leading us to confront the information paradox. In classical physics, information about physical systems is preserved. Yet when matter crosses the event horizon of a black hole, it seems to disappear from our universe. This paradox raises profound questions. If information is lost, does that violate the fundamental tenets of quantum mechanics? Or is there a way for this information to be recovered, perhaps encoded in the Hawking radiation itself? The debate continues, with prominent physicists offering various perspectives. Some, like Leonard Susskind, argue for the holographic principle, suggesting that information is not lost, but rather stored at the event horizon, much like a hologram encodes a three-dimensional image in 2 dimensions. As we journey through these concepts, we find ourselves yearning for a unified theory of physics, a grand framework that elegantly reconciles the principles of quantum mechanics and general relativity. The search for such a theory has become a defining quest in modern physics. Could it be that the very fabric of space and time is woven from quantum threads, with black holes serving as pivotal points of transformation? Imagine a universe where the rules governing the cosmos are not merely a patchwork of theories, but rather a coherent symphony of understanding. As we ponder these profound ideas, we are reminded of the universe's infinite mysteries and the remarkable individuals who have dedicated their lives to uncovering them. The quest to understand black holes and their relationship with quantum mechanics is not just a scientific endeavor, it is a journey into the very heart of existence itself. In the words of Albert Einstein, "The most incomprehensible thing about the world is that it is comprehensible." This journey invites us to embrace the wonder of the cosmos, to imagine the unseen forces that shape our universe, and to remain curious about the answers that await us in the cosmos' vast depths. The role of black holes in the universe's evolution is nothing short of profound. These enigmatic entities, born from the explosive deaths of massive stars, serve as both creators and destroyers in the cosmic dance. As they form, they draw in surrounding matter, crafting a gravitational well that influences the very structure of galaxies. Picture a galaxy as a vibrant city, where black holes act as the gravitational anchors, holding the swirling stars and gas in a delicate balance. Without these monumental forces, galaxies might drift apart, failing to coalesce into the beautiful structures we observe. The merging of black holes, as witnessed through gravitational waves, exemplifies this cosmic evolution. Emitting ripples in the fabric of space-time, these events not only reveal the existence of black holes, but also provide insight into their formation and growth. The observation of two black holes colliding paints a vivid picture of the universe's dynamic nature, where creation and destruction coexist in a continuous cycle. Such phenomena challenge our understanding of gravity and space-time, pushing the boundaries of our theories and compelling us to seek deeper truths. At the intersection of black holes and quantum mechanics lies a vast expanse of curiosity. This convergence has sparked countless discussions, debates, and explorations among scientists. Quantum mechanics, with its probabilistic nature and strange behaviors, stands in stark contrast to the deterministic realm of general relativity. How can we reconcile these two pillars of modern physics? Could it be that the very essence of black holes holds the key to bridging this divide? Consider the implications of Hawking radiation, a fascinating concept proposed by Stephen Hawking. It suggests that black holes are not entirely black, but instead emit radiation due to quantum effects near the event horizon. Imagine a tiny flicker of light escaping from the darkness, a whisper of energy that defies the suffocating grasp of gravity. This radiation, while minuscule, hints at a deeper connection between black holes and quantum mechanics. If black holes can emit energy, what does that mean for the information that they consume? As Hawking eloquently put it, black holes are not the eternal prisons they were once thought to be. Things can get out of a black hole both in and out. This statement encapsulates a paradigm shift, inviting us to reconsider the very nature of these cosmic giants. If Hawking radiation allows for the possibility of information escaping, we must explore how this could resolve the information paradox that haunts the study of black holes. The information paradox poses a tantalizing question. Can information truly be lost in the depths of a black hole? If we accept the notion that information is a fundamental component of reality, its potential disappearance challenges the core principles of quantum mechanics. In a universe governed by quantum rules, the idea that information could simply vanish into oblivion seems incompatible. This paradox has ignited debates among physicists, each offering their insights into the nature of reality and the role of black holes within it. One perspective comes from the holographic principle, suggesting that all information swallowed by a black hole is encoded on its event horizon, much like a DVD stores video data. This theory offers a glimmer of hope, proposing that although matter may disappear into the black hole, its information remains preserved on the surface. Imagine the event horizon as a cosmic imprint, a canvas that captures the essence of everything that has fallen into the black hole's grasp. This idea challenges our traditional understanding of dimensions and reality. It suggests that our three-dimensional universe may be an illusion, a projection of information encoded on a distant two-dimensional surface. This notion, while mind-bending, opens the door to a new understanding of the universe, where black holes become not just annihilators, but also keepers of information. As we delve deeper into the quest for a unified theory of physics, the interplay between black holes and quantum mechanics becomes increasingly vital. Can we weave together the intricate threads of relativity and quantum mechanics into a single tapestry of understanding? The pursuit of such a theory has been the driving force for many renowned physicists. Consider, for example, the words of Michio Kaku. The universe is like a symphony, and we are trying to find the right notes to create a beautiful harmony. This sentiment captures the essence of scientific inquiry, where the quest for knowledge becomes a melody that resonates through the cosmos. The search for unification is not merely an academic exercise, it is a deeply human endeavor, rooted in our desire to comprehend the universe's mysteries. The quest for a unified theory has led to various approaches, each more imaginative than the last. String theory, for instance, proposes that fundamental particles are not point-like dots, but rather tiny, vibrating strings. These strings interact with one another, shaping the fabric of reality itself. Could it be that black holes, with their immense gravitational pull, serve as laboratories for testing these theories? Their environments, extreme and unforgiving, could hold the secrets we seek. As we contemplate these ideas, we are reminded of the infinite possibilities that lie ahead. The universe invites us to explore, to probe the unknown, and to embrace the mystery of existence. What lies beyond our current understanding? How do black holes influence the very fabric of space-time and the emergence of life? With every new discovery, we inch closer to unveiling the cosmic puzzle. Whether it's the detection of gravitational waves or the observation of Hawking radiation, each piece contributes to a larger narrative that connects us to the universe. We are not mere observers. We are active participants in this grand cosmic story. As we stand at the precipice of understanding, the allure of black holes and their connection to quantum physics beckons us to explore further. They are not just celestial phenomena, but gateways to profound truths about the nature of reality. In the words of philosopher and physicist David Bohm, the universe is a single, undivided whole, and everything in it is interconnected. This interconnectedness is beautifully illustrated in the delicate balance of creation and destruction that black holes embody. They are both the end and the beginning, a reminder that from chaos springs order, and from death, new life emerges. As we continue to unravel these cosmic mysteries, we are reminded of our place in the universe, not as isolated beings, but as integral threads in the vast tapestry of existence. The journey to understand black holes and their relationship with quantum mechanics is an odyssey that invites us to ponder the limits of our knowledge and the boundless potential of discovery. It encourages us to embrace the unknown and to remain ever curious as we seek to bridge the gap between the familiar and the mysterious. Each new insight illuminates the shadows of our understanding, guiding us toward a deeper appreciation of the wonders that lie ahead. As we navigate this intricate landscape, let us keep our minds open and our hearts attuned to the symphony of the cosmos, for the answers we seek may reside in the very depths of black holes, waiting patiently to reveal their secrets. The universe, in its infinite wisdom, holds a mirror to our own quest for knowledge, reflecting the beauty of inquiry and the power of imagination. As we ponder the intricate dance of creation and destruction within black holes, we are drawn to the profound effects they have on matter itself. The journey toward understanding these cosmic giants leads us to a fascinating phenomenon known as spaghettification, an experience that reveals the extreme forces at play as objects approach the event horizon. What happens to matter under such intense gravity not only challenges our perceptions, but also deepens our appreciation for the complexities of the universe. In the next chapter, we will delve into the mechanics of this stretching and compressing process, exploring the fate that awaits any object daring enough to cross the threshold of a black hole. Join us as we unravel the mysteries of spaghettification and its implications for the very fabric of existence. Chapter 9. The Fate of Matter, Spaghettification Explained. Imagine standing on the edge of a vast ocean, where the horizon meets a realm of infinite possibilities. This ocean is not made of water, but of the very fabric of reality itself. As we delve into the concept of spaghettification, we find ourselves questioning the nature of existence. Could it be that we are all drifting within a black hole, a part of a swirling multiverse, interconnected in ways we have yet to comprehend? Spaghettification is a term that evokes vivid imagery, conjuring the unsettling idea of matter being stretched and elongated like strands of spaghetti as it approaches a black hole. This phenomenon occurs due to the intense gravitational forces at play. When an object ventures too close to a black hole, it encounters a gravitational gradient, meaning that the force of gravity is significantly stronger on one side than the other. This difference creates a tidal force that pulls the object apart. As objects draw nearer to a black hole, gravity's grip becomes increasingly fierce. Take a moment to imagine this. An astronaut, perhaps, floating serenely in the void, oblivious to the peril that lurks within the darkness ahead. The astronaut feels a gentle tug at first, then a relentless pull as the black hole's immense mass warps the space around it. This is where the magic and terror of spaghettification truly come into play. The stretching and compressing of matter occurs as the object enters the zone of influence of the black hole. The closer it gets, the more pronounced these forces become. The feet of our imagined astronaut experience an overwhelming force compared to their head, pulling them apart, while the pull of gravity increases exponentially. This process is not merely a theoretical exercise. It is a natural consequence of the laws of physics as we understand them. What happens to the matter that crosses the event horizon, that critical boundary beyond which escape is impossible? As one crosses this threshold, known as the event horizon, the fate of that matter becomes sealed in the cosmic tapestry. According to physicist Stephen Hawking, black holes ain't as black as they are painted. He suggested that black holes may emit radiation, albeit in very subtle ways. This raises fascinating questions about the nature of matter and energy inside a black hole. As the matter is drawn inexorably towards the singularity, it finds itself in a state of transformation. The intense gravitational forces compress and stretch it beyond recognition. Imagine the atoms of the astronaut's body. What was once a cohesive form is now disassembled into its constituent particles, stretched into thin filaments of energy and matter. This process serves as a reminder of how the universe can reclaim and repurpose what we perceive as solid. But let us not limit ourselves to just the physical aspect of this transformation. Consider the philosophical implications. What does it mean for the essence of existence when matter is torn apart at the seams? Might it be that the very act of spaghettification serves as a bridge between life and the cosmos, a reminder that all things are transient? As we reflect on the journey into a black hole, we can visualize not merely destruction, but a metamorphosis, an interaction that transcends our understanding of life and death. It is a profound representation of the universe's relentless drive towards complexity and change. Imagine if, by some twist of fate, the shredded remnants of matter were to emerge in a different form, perhaps in a distant universe, or re-enter another cycle of creation. The concept of spaghettification invites us to explore the very boundaries of our understanding. It asks us to consider the delicate balance between creation and destruction, a cycle that governs not only black holes, but the universe itself. As we ponder these mysteries, we can find solace in the notion that perhaps the fate of matter is not an end, but rather a transformation into something new, something unimaginable. In this cosmic dance, we are left with questions that echo through the vastness of space. What if, as some multiverse theories suggest, we are not just within a single black hole, but nestled within multiple layers of reality, each black hole potentially serving as a gateway to another universe, each universe shaped by the remnants of spaghettified matter? The implications are staggering. If every black hole is a portal, then perhaps the remnants of our once cohesive forms could lead to new beginnings in alternate realities. Imagine the endless possibilities that arise from such an idea. where the fate of matter is not just a story of dissolution, but a prelude to rebirth. As we contemplate the nature of spaghettification and the forces at play in a black hole, we are reminded of the fragility of existence. The universe, in its infinite complexity, holds secrets beyond our comprehension. Perhaps, in embracing the unknown, we can find peace in the idea that even in the face of destruction, there exists a potential for something extraordinary to emerge. As we journey deeper into this cosmic mystery, we find ourselves drawn to the very essence of matter and its fate. What lies beyond the event horizon? Is it merely the end, or is it a transformation into a new state of being? The answers remain tantalizingly out of reach, inviting us to explore further. In the end, spaghettification represents more than just a scientific phenomenon. It embodies the interplay of matter and energy, life and death, creation and destruction. It beckons us to look beyond the surface, to consider the profound connections that bind us to the cosmos. As we ponder these grand themes, let us hold on to the beautiful enigma of existence, where every end may indeed be a new beginning, waiting patiently in the depths of the universe. In the shadow of a black hole, the very fabric of reality bends and stretches, creating an atmosphere that is both terrifying and awe-inspiring. Spaghettification, the process by which objects are elongated and compressed into thin strands as they approach a black hole, illustrates the powerful forces at work in these cosmic giants. This phenomenon occurs due to the stark difference in gravitational pull experienced by different parts of an object, leading to a dramatic stretching effect. Imagine holding a piece of dough in your hands, pulling it apart until it becomes a long, thin strand. Now consider that instead of dough, it is a star or a planet, being inexorably drawn toward the event horizon, where the gravitational influence is so intense that nothing can escape. As the object nears the black hole, the gravitational gradient becomes increasingly steep. This is not merely a gentle tug. It is a ferocious pull that can tear apart the very bonds holding matter together. The forces involved are immense, dwarfing any experience we could encounter in our daily lives. Renowned physicist Stephen Hawking once said, "Black holes are where God divided by zero." This playful remark emphasizes the enigmatic nature of black holes, where our understanding of physics seems to break down, and the laws we hold dear begin to unravel. What happens to matter that crosses the event horizon? This boundary, often described as a point of no return, marks a critical threshold where the escape velocity exceeds the speed of light. Once matter crosses this boundary, it is said to be lost to the universe as we know it. It is as if the universe holds its breath, waiting for the fate of the matter to unfold in the depths of the black hole's singularity. The singularity is a point where density becomes infinite, and the known laws of physics cease to apply. Can we even begin to fathom what lies within this mysterious core? The truth is that we may never fully understand the transformations taking place there. Imagine for a moment the journey of a star that ventures too close to a black hole. As it approaches, the relentless gravitational pull begins to stretch it, turning it into a thin, elongated shape akin to a strand of spaghetti. This is where the term spaghettification originated, a vivid descriptor of the fate that awaits any object that dares to venture too close. The star's once cohesive structure is dismantled, its components pulled apart as if they were mere threads in a cosmic fabric. What must it feel like to be torn asunder by the very forces that govern the universe? Consider the implications of such a transformation. If spaghettification is the fate of matter, what does it mean for our understanding of existence? Could it be that the atoms and particles that once formed a star are not truly lost? Instead, they may find a new existence in an alternate reality woven into the grand design of the multiverse. This tantalizing thought invites us to ponder our place in the cosmos. Are we mere spectators of this cosmic ballet, or are we intrinsically linked to the fates of stars and black holes? As we delve deeper into the nature of spaghettification, we must also consider the role of extreme gravity in shaping our universe. The effects of such gravity extend far beyond the immediate vicinity of black holes. It influences the orbits of stars, the formation of galaxies, and even the very structure of space-time itself. When we gaze at the night sky, we are witnessing the remnants of these cosmic dramas, the echoes of interactions that took place billions of years ago. The universe is a vast, interconnected web, where the fate of one element can impact countless others. As physicist Albert Einstein once remarked, "The most incomprehensible thing about the world is that it is comprehensible." This profound observation speaks to the intricate relationships that bind the cosmos together. In contemplating spaghettification, we are drawn into the heart of these relationships, where matter is not merely a collection of particles, but a dynamic entity undergoing constant transformation. The process challenges our perceptions of existence, inviting us to reconsider the boundaries of life and death. What if, in the act of being drawn into a black hole, matter is merely undergoing a metamorphosis? Imagine the potential for new forms of existence emerging from such a process. Could the remnants of a once bright star contribute to the birth of a new celestial body, perhaps even a new solar system? The cyclical nature of cosmic creation suggests that every ending may indeed serve as a precursor to a new beginning. This notion is beautifully encapsulated by the words of physicist Carl Sagan: "The cosmos is all that is, or ever was, or ever will be." As we explore the fate of matter and the phenomenon of spaghettification, we find ourselves at the intersection of science and philosophy. The questions raised by this journey are profound and unsettling. What does it mean to exist in a universe where transformation is not just possible, but inevitable? Are we simply stardust, bound by the laws of physics, or is there a greater narrative at play, one that transcends our understanding? As we weave through the cosmic landscape, let us embrace the mystery of spaghettification, the delicate interplay of forces that shape our universe. It is a reminder that existence is not static but a fluid journey, where matter is continually transformed, reborn, and reimagined. The threads of reality stretch and twist, echoing the ancient tales of creation and destruction that resonate through the ages. In the depths of this cosmic mystery, we find a soothing reassurance. Even as we contemplate the fate of matter, we can find solace in the knowledge that the universe is alive with possibilities. Each moment is a fleeting glimpse into the grand design, where the dance of matter and energy continues, inviting us to explore the fabric of existence with wonder and curiosity. As we ponder the fluid nature of existence and the transformative journey of matter, we arrive at a pivotal juncture, one that leads us into the enigmatic realm of black holes. These celestial giants serve not only as cosmic voids, but as powerful engines driving the evolution of the universe. Their duality embodies the delicate balance between creation and destruction, shaping galaxies and influencing the very fabric of cosmic architecture. In the next chapter, we will delve deeper into the profound role black holes play in this grand narrative, exploring how they contribute to both the birth of new stars and the demise of others. Join me as we unravel the mysteries surrounding these formidable entities and their indelible impact on the cosmos. Chapter 10. The Cosmic Role of Black Holes, Creation and Destruction. As we delve into the cosmic role of black holes, we find ourselves contemplating the delicate balance between creation and destruction in the universe. Black holes, those mysterious entities born from the remnants of massive stars, are not merely tombs of collapsed matter. They serve as engines of cosmic evolution, shaping galaxies and influencing the very fabric of the cosmos. Imagine standing on the edge of a swirling galaxy, gazing into the heart of a supermassive black hole. This black hole, potentially millions or even billions of times the mass of our Sun, exerts an incredible pull on the surrounding stars and gas. It is here that one can witness the profound influence of black holes on galaxy formation. As matter spirals into the black hole, it heats up, emitting brilliant jets of energy that can illuminate the surrounding space. These jets, propelled by the intense gravitational field, can trigger the formation of new stars. In this interplay of creation and destruction, black holes are pivotal architects in the cosmic landscape. The role of black holes extends beyond mere creation. They are also agents of destruction, capable of consuming entire stars and planets. Yet, within this consumption lies a paradox. As they destroy, they also facilitate the birth of new structures in the universe. The gravitational force of a black hole can pull in surrounding gas and dust, compressing it and igniting nuclear fusion in nearby stars. This process not only fuels the life cycle of stars, but also enriches the interstellar medium with heavy elements, which are crucial for the formation of planets and, ultimately, life itself. One might wonder how this intricate relationship between black holes and galaxies unfolds. The answer lies in the delicate balance maintained by the gravitational forces at play. As black holes grow, they influence the dynamics of their host galaxies, dictating the movement of stars and gas within. The interplay of stellar winds, supernovae, and the gravitational pull of black holes creates a cosmic dance, where the birth of stars is often accompanied by the demise of others. This cosmic symphony is characterized by cycles of destruction and rebirth, each note resonating through the vastness of space. As we look to the future, the exploration of black holes presents both thrilling opportunities and unanswered questions. Scientists are eager to deepen their understanding of these enigmatic entities and their role in the universe. What happens to matter as it approaches the event horizon? How do black holes interact with dark matter and dark energy? These questions tantalize researchers, driving them to develop new technologies and methods for exploring the mysteries of the cosmos. The implications for space travel are profound. As we grapple with the challenges of navigating black hole environments, we must consider the ways in which these cosmic giants could shape our journeys through the stars. Imagine a future where spacecraft can harness the gravitational pull of a black hole to slingshot across the galaxy, utilizing its immense energy, rather than falling prey to its destructive capabilities. This vision, while still within the realm of science fiction, hints at the potential for revolutionary advances in our understanding of physics and the universe. In the realm of theoretical research, scientists like Stephen Hawking have laid the groundwork for exploring these celestial phenomena. Hawking once said, "The black hole is a place where the laws of physics as we know them break down." His insights challenge us to rethink our understanding of the universe and to question what lies beyond our current grasp of reality. The quest to unravel the secrets of black holes is a testament to human curiosity and our desire to comprehend the cosmos. As we ponder the cosmic role of black holes, we are reminded of the delicate interplay between creation and destruction. Each black hole is a reminder of the universe's cyclical nature, where death gives rise to life and where the remnants of the past fuel the birth of the future. The more we learn, the more we realize how much remains to be uncovered. What mysteries lie hidden within the depths of these cosmic giants? What revelations await us as we continue to explore the uncharted territories of space? In this vast expanse, black holes serve as both guardians and destroyers, shaping the destiny of galaxies and influencing the evolution of the universe. As we push the boundaries of our understanding, we are drawn into a deeper appreciation of the complexities of existence. The future of black hole research is bright, illuminated by the possibilities of discovery and the promise of understanding the universe on a grander scale. The journey into the heart of black holes invites us to reflect on our place in the cosmos. As we gaze into the night sky, we are reminded of the interconnectedness of all things, the delicate balance of creation and destruction that governs the universe. In contemplating the cosmic role of black holes, we embrace the mysteries of existence and the wonders that await us in the great expanse beyond our world. Black holes, with their enigmatic allure, are not merely cosmic vacuum cleaners, consuming everything in their vicinity. Instead, they operate as powerful engines of cosmic evolution, playing a pivotal role in orchestrating the grand symphony of galaxy formation and growth. Imagine, if you will, the universe as an artist, using black holes as both the brush and the canvas, crafting intricate structures that evolve over billions of years. As galaxies form, their central regions often harbor supermassive black holes, whose gravitational pull draws in gas and dust. This accretion process ignites a brilliant display of energy, transforming material into light. The luminous emissions from these regions serve as beacons, illuminating the dark cosmic void. Astronomer Carl Sagan once said, "The cosmos is all that is, or ever was, or ever will be." Such a statement echoes in the vastness of space, reminding us that black holes are crucial players in the cosmic narrative, fostering the very stars that populate our night sky. The birth of stars is intimately tied to the influence of black holes. In the chaotic dance of interstellar gas, black holes can trigger the collapse of molecular clouds, facilitating star formation. Picture a vast nebula swirling with potential, where the gravitational influence of a nearby black hole initiates a cascade of events, leading to the birth of new stars. This process exemplifies the balance between creation and destruction, as elements are forged in the hearts of stars only to be recycled into the cosmos upon their demise, feeding future generations of celestial bodies. Yet, how do these titans of gravity maintain their influence over such vast distances? The answer lies in the phenomenon of gravitational waves, ripples in space-time that emanate from cataclysmic events involving black holes. When two black holes collide, they emit bursts of energy that ripple across the fabric of the universe, much like a stone cast into a still pond. These waves carry information about their origins, acting as a cosmic messenger. As physicist Kip Thorne eloquently stated, gravitational waves are the most powerful waves in the universe. They tell us about the fabric of space-time itself. As we delve deeper into the role of black holes in galaxy formation, we cannot overlook the intricate relationship between these cosmic behemoths and their host galaxies. It is believed that supermassive black holes influence the growth and structure of galaxies through feedback mechanisms. The energy released during the accretion of matter can heat surrounding gas, preventing it from coalescing into new stars. This interplay raises fascinating questions. Are black holes the architects of galactic evolution, or do they merely respond to the dynamics of their environment? The balance between creation and destruction also manifests in the fate of galaxies. As galaxies collide and merge, the central black holes may also converge, giving rise to even more massive entities. In this cosmic ballet, the resulting black hole can become a powerful source of energy, expelling jets of particles at near-light speed. These jets can influence star formation rates in surrounding regions, further intertwining the fates of black holes and galaxies. However, the story does not end here. The very existence of black holes invites us to ponder the future of the universe. What lies ahead in this vast cosmic journey? With every new discovery, we inch closer to understanding the ultimate fate of these enigmatic entities. Will they continue to dominate the cosmic landscape, or will they eventually fade away, leaving behind a universe teeming with light and life? Future research directions are as boundless as the universe itself, with unanswered questions that tantalize the imagination. As we refine our observational techniques and enhance our understanding of gravitational waves, we open new doors to exploring the nature of black holes. Will we uncover the secrets of their interiors? Or perhaps even identify the elusive connection between black holes and the fabric of space-time itself? Consider the vast array of technological advancements that lie ahead. The James Webb Space Telescope, with its unprecedented capabilities, promises to unveil the mysteries surrounding black holes and their role in the early universe. The exploration of distant galaxies, still shrouded in cosmic dust, may yield insights into the formation of black holes, offering clues about their inception in the primordial cosmos. Moreover, the development of future gravitational wave observatories will allow us to capture events as they unfold, providing real-time data on black hole mergers and their consequences. Imagine standing at the forefront of discovery, witnessing the birth of new knowledge as we listen to the echoes of the universe. As we reflect on the implications of black holes for space travel, the very nature of our exploration endeavors shifts. Can humanity's future voyages venture near these cosmic giants? What technologies might allow us to traverse the perilous environments surrounding black holes? The thought of sending spacecraft into the vicinity of a black hole is both exhilarating and daunting. The potential for scientific discovery is immense, yet the risks are profound. An intriguing prospect lies in the harnessing of black holes, immense gravitational energy. Theoretical physicists ponder the possibility of leveraging black holes as power sources for future civilizations. Picture a future where we utilize the Hawking radiation emitted by black holes, transforming it into energy that propels humanity into the stars. In contemplating these possibilities, we are reminded of the words of physicist Michio Kaku: "The universe is a giant brain, and we are just beginning to understand how it works." As we continue to probe the mysteries of black holes, we engage in a dialogue with the universe itself, seeking to decode the language of creation and destruction. The allure of black holes is not merely scientific, it stirs a sense of wonder that transcends the boundaries of knowledge. They remind us of our humble place in the cosmos, inviting us to explore the unknown while embracing the beauty of the mysteries that remain. In this vast cosmic wilderness, black holes stand as symbols of the dual nature of existence, where creation and destruction are irrevocably intertwined, each giving rise to the other in an endless cycle. As we embark on this journey of discovery, let us remain open to the wonders that await us, embracing the unknown as we seek to illuminate the darkest corners of the universe. In the dance of creation and destruction, we find not only the essence of black holes, but also the essence of our own existence within the boundless cosmos. As we conclude our exploration of black holes, we are left with a profound appreciation for their dual role as architects of the universe, shaping both creation and destruction. These enigmatic entities challenge our understanding and beckon us to push the boundaries of scientific inquiry. With each technological advancement, from the James Webb Space Telescope to future gravitational wave observatories, we edge closer to unraveling their secrets, fostering a dialogue with the cosmos that is both exhilarating and humbling. In contemplating the mysteries of black holes, we not only confront the vastness of space, but also reflect on our own place within it, inspired to embrace the unknown and the potential it holds. As we journey onward, let us carry the wonder of these celestial giants, recognizing that in their depths lies not just the end, but the promise of new beginnings.